lab? Do a lab, any lab. Is there uncertainty? Yeah. We now know for sure, right, that there's got to be some sort of uncertainty. So we don't necessarily know exactly what our answers are. Does that mean we stop doing labs and we're all done and we just learn what has been written and take it as truth? No. Oh, that would be silly. That would be silly. We just need to be able to acknowledge the errors, right? So we need to be able to name them and talk about them a little bit more thoughtfully, okay? So we're going to talk just for a little bit here about error and uncertainty. Okay? So there are some very specific types of error that can happen when you're doing a lab or when you're collecting any sort of data. What types of error might occur? Like maybe when you're dropping a ball and then watching to find out how high it goes, for example, if that's something that you can imagine having done. What types of things could happen?
It could just be like human error. Like instead of dropping the ball at the same place every single time you drop it, like at a slightly different place every single time, just because maybe it's an accident or maybe your ruler isn't that great or whatever.
Okay. Were you going to say something more? I feel like I just cut you off by saying that, sorry.
No, it's okay.
Okay, okay. So I think you actually kind of had two different pieces in there. So, and we're going to talk in a minute about the whole concept of human error, okay? That will be the last time that that phrase is uttered in this room for the remainder of forever. Fair? Okay? Human error means nothing. It means, and I'm not trying to say, Gemma, that you were, but I'm using you as an example because I am certain, I have no uncertainty about the fact that you all want to use that, or at least many of you do, because it's an easy thing to say, right? Oh, it didn't work out. Human error. Like, what is that? It doesn't mean anything. It means I'm not creative enough or I'm not thoughtful enough to think about what really went wrong. I just screwed up. Like, that's no. We need to like think about it. So, the first example that she gave was like maybe not dropping it from the same spot every time. Right? So maybe most of the time you're dropping it from one place, and then one time you like, I don't know, you get a tickle in your nose and you move your hand a little bit or something like that. What would we call that kind of error? Any idea? Any idea? Does it happen every time? No. It's called a random error. Okay. A random error is one where the values or the measurements fluctuate. Okay? So as you're taking data from a certain height, you take it and you get different things. How do we get rid of, or can we get rid of or minimize random error? As a good experimental scientist, how can you get rid of completely random error?
No.
Is it possible? No, not possible, right? But can you minimize it?
Yeah.
How would you go about minimizing random error?
Like if you have two people working on a project, you have the same person dropping the ball every time, so if they're dropping it wrong every time, they're wrong every time.
Okay.
And
Is that random error, or is that a different kind of error that we may be going to talk about a little bit?
Probably different kind.
Yeah. So tell me, I want to know how to get rid of this one, because we'll talk about that in a second, because that's huge.
Could you, 3 trials?
3 trials.
Average them?
Or what if you have 3 trials and they're all really different?
Just keep doing it.
4 trials, 5 trials, 7, 12, 37, something like that, right? Yeah, lots of trials. So it can be minimized by multiple trials. And it's really important to recognize, I think a lot of times, again, in this, bubble that we live in as students, middle school, high school science students, you do the trial 3 times, and it's got to be right. No. You do it enough times so that you get good data. And you have to think about it to figure out if you've gotten good data. So if you have 3 points and they're all almost the same, that's probably okay. If you have 3 and 2 of them are the same and one of them is different, what does that imply about the one that is different? There might be something wrong with that one, right? So does it make sense to average that one in with the 2 that seem right? No, what would we do instead? Or what would be a better choice of things to do? Do it again. And again and again and again, right? I was having this conversation with one of my 8th grade classes. We were talking about, we weren't having it like in this formal way, but we were kind of talking about it. And he said that his teacher last year, science teacher last year, told him that statistically, somebody has figured out that the best number of trials to do every time is 30. That's a lot of trials. Would you agree? Right? Like that would make our labs take a whole lot longer than we have time for. I'm not saying you need to do 30 trials every time. I'm saying that some statistician somewhere who is getting their, PhD or whatever and needed something to do, figured out that 30 was like the place where if you do more than that, it's like a waste of your time. Okay? But you have to be smart about it. Figure out how many trials you need to do. Okay? So we're going to do multiple trials, enough trials to make things good, whatever that means. Okay? And then, so we get, 4 or 5 that have about the same number. And then what do we do with those values?
You average them.
Yeah, we're going to average. We always average the trials with the same initial conditions. Sometimes I don't specify that, and then some of my lovely students will they'll have like a huge thing of data, right, from dropping it at 30 and dropping it at 40 and dropping it at 50. Then they average all of them together. They come up with one number, and I'm like there's a you see what I'm saying? Like that, we're not thinking about what's going on scientifically there. So you're averaging all of the things that you dropped at 40 centimeters, for example, okay? That's what we're talking about. Okay, so that's random error. That's how we get rid of it. Now, Charlotte, you mentioned another flavor of error, and Gemma had kind of talked about it. It was, tell me more about what you were saying about.
Well, like when we were doing the drop the ball thing, like I was looking how high it went, and I guess if I had done it from like, oh well, I'll take it the number it was closest to on the top, or the numbers it passed last. Like you have to decide how you're going to do it and do the same every way, so that if you're wrong, you'll still have the same like curve or slope.
Does that do you see what she's saying? Yeah. So you got to make a decision, right?
Yeah.
I'm going to look at the bottom of the ball every time, okay? Or I'm going to sit on the floor and look at it from there as opposed to standing up. And the idea is that you want to do it the same way every time, and you want it to be you every time and not somebody different every time looking at it, because that would be crazy. But does that mean that she's exactly right? No. But it means that we're not going to have this random error. What kind of error are we going to have now? You know what that's called? Starts with an S. Systematic, yeah. So systematic error is a little bit harder to detect if you're just looking at a data table, because the values are consistent. But they're not necessarily right, which is a little bit frustrating perhaps. Okay. What causes systematic error?
When your tools like aren't super precise or accurate.
Okay, so yes and no. So I'm gonna make a list of like bad words up here, or bad phrases. Human error. is one I don't ever want to see. Okay. Another thing that makes me kind of want to cringe and throw stuff. I'm not a violent person. I'm a really friendly person. But like I'm like ah. Like what would we call it? Like bad equipment or bad measurement tools. Okay, I give you a meter stick, and I'm not picking on you. This is like from historical experience, right? I give you a meter stick to measure these things. Will that be accurate enough for what we're doing? Yeah, if you use it right. Okay? If you use it right, it will be fine. So don't tell me that my meter stick is subpar. I mean, if I give you like a gnarly stick that's like not straight and like has random lines on it that don't make any sense, then okay. Then like, but no, they're fine.
I mean, like they don't go to the billion, which is what they were talking about in the paper.
It's true, but are your eyes able to resolve to the billionth, my friend?
Well, also, like I saw other groups were like using their phone, and theirs would be more specific than if you used your eyes.
It's true. So why didn't you use your phone?
Well, because I didn't think of that.
Oh, is that my fault?
Yeah.
No. Not so much. So this is the deal, is that I don't want you ever on a lab, and Mr. Feynman doesn't want you ever on a lab either, to blame the equipment. Okay? Here's the nice thing about this, though. There are two pieces to it. The first thing is that we need to make sure, I'm going to write primary causes here so I don't get too far off. Primary causes of this crazy stuff. Okay? One is the misuse of equipment. Human error. Oh, but let's be a little more specific. Like maybe the ruler wasn't standing up straight, right? Something like that. That's what we're talking about. Or, not so much in the case of ruler, but like in the case of like maybe a balance or something like that, maybe it's not calibrated, so it's miscalibrated. So that would be, or that could be like you taped the meter stick to the table or to the wall, but there was a little bit of space at the bottom, right? Or if you tape it to the wall, there's this little lip at the bottom here, right? So it's not going to be exactly straight, that kind of stuff. Now, does that mean that the answers are wrong? Yeah, a little bit. Is it going to matter a whole lot? No. No. And we accept that there is some systematic error. That's okay. Another reason or another cause of this, like when I'm dropping something to measure the acceleration due to gravity, okay, I can measure how long it takes. I measure the height. Life is good. There's something I'm not taking into account. What's that? Well, there's reaction time. That's for darn sure, right? That's definitely going to live in here, right? So making sure you have the same person taking the data, right? There's also this thing that helps us to live and breathe. This stupid air stuff, right? That also causes friction. Jeez. Okay? It's going to affect our data a little bit. A lot? No. A little bit, yeah. So making assumptions. I'm going to say like no friction. These are the specific things that lead to systematic error. So just writing something like human error is totally silly because you're not thinking. I want you to know exactly why. Like, or maybe not know, but give some ideas of why. Systematic error is kind of hard to quantify. Okay. But it is much easier to identify. I'm going to say when data is represented graphically. And then there's one more that I just want to make sure I throw in there because it is important. The last kind of error is reading error. And this is the error that you can blame on the equipment, right? The equipment was not good enough. But we also can acknowledge this very easily. Okay? If I know that my meter stick goes to the millimeter, then I should be able to be accurate within a millimeter, right? Maybe. Maybe not if I'm just glancing at it. Maybe I'm only accurate to a centimeter. This is where you acknowledge that there's that uncertainty, okay? So the reading error is inherent to the measurement tool. Okay. It cannot be improved by multiple trials. Okay. And this is the type of error that has to be recorded. This is where all of that crazy sig fig stuff comes from. Okay? You remember having sig figs conversations. If you were in chemistry, you're like, oh my gosh. Now let me tell, right? Is that true? You're like, oh. Let me tell you, I'm gonna tell you the big picture, little picture. Big picture, sig figs matter. You guys all know what I mean when I say sig figs? Significant figures, number of decimals, et cetera, et cetera. Yes, this is like, okay, we're not, okay. They matter, especially when you're doing labs. But I'm not going to spend oodles and oodles of time getting cranky about it because there's much more important things in physics than just worrying about sig figs. Does that make sense? So I want you to acknowledge that they're there, acknowledge that they are important, and then let's not get all anxious and cranky about them, okay? Reading error must be recorded. And it's really easy to record. Okay? You record the smallest division. So on that meter stick, the smallest division is a millimeter, right? Okay? The reading error, if you have what we call an analog instrument. Do you guys know what the opposite of analog is? Digital. So we've got analog, we've got digital. So digital is where you're going to get like a readout. Okay, so it's like an electronic balance. Okay? Or a stopwatch. Okay? For a digital instrument, the recorded number is going to just be the smallest division. A tenth of a second or whatever it is. For an analog thing like a meter stick or a triple beam balance, it's half of the smallest division. There are really good reasons for all of that. I'm not going to get into it right now, mostly because I want to move on and do things that are more exciting. But I'm just letting you know that that's true and we'll apply it soon. Is that fair? If you want to get into a deeper discussion with me about it, I'm very happy to. Like I said, I mean, there are good reasons for these rules. I just don't want to spend all of our time doing that because I'd rather do other physics. Are we okay so far? Okay. So what we're going to do, we're going to pause here so that next time you do a lab, you're like, oh, I didn't want to make that same mistake again. So just on the design portion, what observations did you make? Things that you either saw on labs that you graded or saw on labs saw in your lab when you got feedback? Go.
One of the graphs didn't have an origin, like start at 30 and then 10, 50.
Okay.
I wondered about that.
Yeah, so that's going to go in the data collection and processing. Aspect 3, I would recommend that either when you're graphing, you start at the origin, or if it doesn't make sense to start at the origin because your numbers are going to be like crazy big, you can use the little jagged lines but you have to use the jagged line so that we know that there's a break. You guys know what I'm talking about with that? Okay? Because if you just start at 15 here, then I'm going to be like, well, what are you doing? Origin should be 0, 0, right? Other notes on the design right now? Things that you saw? Yeah.
Well, it's like easiest, I think, to like when you're grading it to see if someone explicitly says like, oh, our design was this and this is how we did it and we used all of these things. It's really hard to find.
Yes. It is just fine to be explicit. Okay? You can use bullet points. It doesn't have to be all written in prose. That is fine. As long as it's clear to you what's going on. Okay? Okay. I'm going to pause there. I want to talk about this for like another 10 minutes. You're not going to stay for 10 more minutes, are you? No. So, I want you to hold on to these labs. I have to give you one more thing because you do have some homework today, and the homework that you have comes from me, so you can't go anywhere. Hold on to these labs and hold on to that rubric because we're going to talk about it next time at the very beginning, okay?